There are costs.
So it's my pleasure to it's my pleasure to have Rohit Vaish with us. Rohit Vaish is the faculty member at Okay. So it's my pleasure to have Rohit Vaish with us. Rohit Vaish is a faculty member at CNC and IIT Delhi, as well as the IIT School of AI. Rohit is from ISC and she was a postdoc at RPI, DIFR sometime. In spirit, not physically, but yeah. So Rohit works in computational social choice. He's been part of some very exciting discoveries in this field. And he's going to be telling us about one of these for the best of both worlds.
Thank you so much, Umar. Thank you, Raghu, and thank you everyone for having me here. It's such a, it's always a pleasure to be here, and I'm especially glad to be talking to you all today. So I will be talking about best of both worlds in pair division, and just to give you a one-line summary of this work. So this work is about a problem in economics, specifically the resource allocation problem. So we are going to be talking about a bunch of resources, a bunch of agents who have preferences, and we would like to allocate these resources fairly, whatever fair means. And we will see that, techniques that we often think about in computer science, like randomization and approximation, they will very meaningfully come together to give us a nice economic insight. Okay, so that's if you take nothing away, just remember that, some combination of computer science and economics is going to show up. All right. So this is based on a paper called, Best of Both Worlds, ex-ante and ex-post fairness and resource allocation. This is joint work with Haris Aziz from New South Wales, Rupert from Virginia, Nissel from Toronto, and this appears in the operations researcher. So the kind of resources that we will be thinking about, they are actually called indivisible or discrete resources. And just to give you a few examples, so imagine you have an inheritance, right, over which a bunch of siblings are fighting or contesting. Now they all may have different preferences over the items in the inheritance. Someone might want the house, someone might want the car, someone might want the very expensive painting, and so on. And you would like to divide the items of the inheritance among these stakeholders in a fair way, whatever fair means, subject to their preferences. Now, the interesting thing about these kind of resources is that they are discrete, meaning the entire resource should go completely to one person or the other. You can't fractionally allocate or cut up the resources and give it to one group, because then you destroy their value. Okay, so that's a very special feature of resources that will actually guide many of the fairness notions that we speak about. Another example is, let's say, we will flip coin the design. Absolutely.
So one general question is, why can't you just sell all the items, collect the money, and distribute it?
Because people have utility for the items, not so much for the money that it buys. So you may have like some sentimental value for the house that no amount of money can replace.
This is general question.
Yeah. Yeah. So you really want to assign the items, not the money.
So whatever could be sold is sold, and now the remaining.
Exactly. This is the stuff that we want to buy. And actually, there's no money in the picture. Right? It's just the resources and people with preferences, and we want to allocate it fairly, whatever fair is. So other examples of discrete resources are, say, allocation of seats in university courses. Right, so especially for someone coming from, let's say, an IIT, you have to be fair across various engineering departments. So the best courses should not just go to the computer science people. We have to take into account the mechanical people and the textile people and whatnot. Right. Similarly, we don't want to give the best courses to the fourth year undergraduates. We also have to listen to the second years and third years and so on. Okay. And another example that we sort of very painfully saw over the last 3 years or so is allocation of medical resources, right? Things like medicines and TT kits. Again, you would like to allocate these things fairly across various population groups, right? You don't want to give all the medical resources to the elderly. You also want to take the young ones into account and things like that. So broadly speaking, these are many other examples you can think of. They involve discrete resources. And allocation of discrete resources will pose certain challenges, as we'll see in just a minute. Okay, so here's a very simple model to think about this problem. Okay, So we are given a bunch of agents given by these happy triangles and a bunch of items, discrete items given by these circles A, B, C, D, and E. And these numbers here denote how much happiness each agent derives when it gets that item. Okay, so for example, you look at this number here. This means that if you give blue agent item C, it gets 5 units of happiness, and typically the more the better. Okay. Similarly, item B is worthless for the blue agent, and so on. Now, these are the values over individual items, right? What we will be interested in is actually finding an allocation of these items. So we want to give every item to exactly one person. So like I said, you can't fractionally divide an item. You can't say, okay, half of item A goes to this person, the other half goes to that person. That is not enough. Okay. So what we're looking for is an entity like this, where every item goes to exactly one person. So in this case, A goes to red, blue gets B, D, and E, and item C goes to B. So that's an allocation. And so what I showed to you so far are the values over individual items. When people can get multiple items, you also have to define values over subsets of items. So to define that, I'll assume that the valuations have this additivity property, meaning the value for any set of items is the sum of values of the individual items in that set. So that's an assumption that I'm going to make for this. Yes.
Shouldn't these numbers be normalized? I mean,
Yeah, so I would not. So because I'm going to give you positive results later on, I would say that my algorithms work even if they are not normalized. Although, if for some sort of sanity reasons we want to say okay, everyone has 10 amount of value that they can distribute over items, we can do all that. Everything that I'm going to say still works.
my max happiness can be more than yours. Yeah, exactly. Some people can just be grumpy.
Yeah.
Talking about that taken care of by my algorithms.
Not just parents, parents.
Yes.
Next week.
I don't know. It's going to that, but all right. Okay. So any questions about the model? All right. Cool. So what is fair, right? I've told you what an allocation is, but we would like to find a fair allocation. Well, one very natural notion of fairness is envy-freeness, which informally means that everyone is happy with what they have got, right? And no one envies the stuff that anyone else has got. Okay.
Sorry.
No problem.
What did I do? Why did it become blue?
No, it's fine. It's a right.
Sorry.
Yeah.
I was going there anyway. All right. Okay. Okay. All right. So just to give you an example of what unifies means. So suppose we have these two agents, red and blue, and these three items, and suppose A is given to red and B and C are given to blue. Now, if I am the red agent, if I look at my bundle, I derive a value of 4, right? Whereas if I look at the blue agent's bundle, because of additivity assumption, I derive a value of 3 for the blue agent's bundle. So I like my bundle at least as much as the blue agent, so I don't envy the blue agent, right? Likewise, if I am the blue agent, my value for my own bundle is 6, and I don't have a lot of value for red's bundle, so I don't envy red. So both agents are happy with what they have, no one envies the other, so this is an envy allocation. Okay?
So we look at the entire bundle, not you can't
We are not plucking items out of it. I'm just comparing my entire bundle with the other person's entire. Yeah.
So for general valuation, do NVIDIA allocations exist?
Yes. So thank you. So there are very simple settings in which actually NVIDIA allocations may not exist. Imagine just the two of us fighting over an expensive item. So right. So yeah, it's a very natural notion, right? But it does not pass the existence test. Right. Just to be a bit more formal, so I'll use this notation to define allocations. So here A1, A2, AN denote the bundles of the agents 1, 2, 3 up to n. Okay. And such an allocation would be NV-free if for any pair of agents that you pick, agent I and agent K, it would be the case that I is valuing its own bundle at least as much as it values K is bundle. So it does not envy K. Okay, this should hold for every pair of elements. Okay. Now, as was observed that NVP allocations may not always exist, right? And not only is there an existential downside, there's also a computational downside, which is that if I give you an instance of the fair division problem, and by instance I mean a matrix like this, so that's my input, and I ask you, well, does it admit an NVP allocation? That amounts to solving an NP complete problem. Yeah, it's a very simple reduction from subset star multiplication.
Disaster for a family which has 1,000 children.
No?
If a family has 1,000 children, then competition becomes an issue.
Yeah, I mean, large scale
But it's not everything. It's not
I did not know that application of fair division.
The first non-existence is more because the number of hoods is more than the number of agents.
Yeah, so even
Unless
even
I'm happy with the empty set, this is always going to be a non.
Yeah.
You can come up with a counterexample.
Absolutely, yeah, so the scarcity of goods is not the reason for
Scarcity of goods.
even if you have a lot of goods, it's just that something that's impossible to balance out
Okay,
things.
Maybe you have one good that you want and the others are trash.
Exactly.
okay.
And that's something that's shared by everybody.
Yeah.
Yeah, maybe everyone has a very high value good and others are epsilons and there's no way you can balance it.
Yeah, so basically, if two of them have, so talking about that NP complete thing, right? So if two of them have same valuation, then basically it's the partition problem.
Exactly, so this is hard even if you have only two agents and even if they have identical values. So it's a very strong context.
So, but if things are smooth, like if individual items are, very, compared to the whole sum of things, if individual items are.
Right, so in particular, I mean, one model you could think about is random valuation, right? Let's say all values are drawn uniformly from the 0-1 distribution. Under certain conditions, actually, NVP allocations exist with higher probability in that mode, right? So to get these results, you have to have some kind of skewness in your instances. Yeah.
Both for the non-existent as well as the computation. Both you need skewness in both cases.
I believe you can get non-existence even with very limited amount of skewness.
Okay.
Right? Actually, I mean, so actually you don't, okay, so you don't even need skewness. So imagine, say, 3 items all valued at 1 and just 2 people. So it's just that the numbers don't check out.
No, but then fractionally everybody is 1/3. Right?
Yeah, but we're not allowing fractional allocations here.
No, I mean like the value of one item is still a constant fraction of the total value in the market.
Oh, I see, independent of the number of agents.
Yeah,
and such.
yeah.
So what is the question? I didn't get the question.
So if
That-
you start avoiding the situation, you said that one person highly values something and everything else is trash. If you say nothing is trash, everything has at least some fractional value of the total valuation, then can you?
It may not be a constant, right? Because
Another way around.
they all add up to
Nothing is true value.
nothing is true value.
Nothing is too valid.
Two is somehow properly set here.
No, but so if you have n as an odd number and you have n identical items in two agents, you will not be able to.
Yeah.
Balance it out, right? Someone
So
will
3
get
items
one.
and 2 people, even if they're all valued at 1, it would not work. Okay, any other questions about NVPs? So this is going to be important, so it's no time lost. Alright, okay, so very natural property, but unfortunately it may not exist always, and checking it is also hard. Okay. And whenever we see such bad results, the Vaish response is something of approximations. Okay, so one approximation that people seem to like a lot is something called NVPness up to 1 good, or EF1. And what it says is that you're allowed to have some envy, and it's okay to envy someone else, as long as you can hypothetically remove some item from their bundle and don't envy their residual one. Okay, so your envy is bounded in this sense up to the removal of something. Okay. So just to give an example, suppose again you have 2 agents, 3 items, and this time I'm giving item C to the red agent and A and B to the blue agent. Okay. Now if I'm the red agent, I have a value of 2 for my bundle and 5 for the blue agent's bundle, so I definitely envy blue. But that envy is bounded in the sense that I could imagine that, okay, if item A was not given to the blue agent, then I would not envy the rest of blue's bundle. Okay. And similarly, if you look at Blue's perspective, if it hypothetically removes item C, then again it does not reveal A. Okay. So probably the EFN motion looks a lot like NVPS, except that we are now going to ask that for every pair of agents I and K, there must exist some item J in agent K's bundle, which if you drop, then you'll like your own bundle at least as much as the reduced bundle of the other person. Okay. So, yeah, any questions?
You can always add one to yours and then say.
You could, yeah, you could play around with these kind of approximations. You don't have to remove something. You can say, okay, maybe I'll copy an item to my bundle and talk about approximations of that form. So yeah, there are a few related definitions. But yeah, we'll go with the removal.
Buddhist and economist.
Buddhist and economist. So this is a paper from the Journal of Political Economy 2011, very influential paper, as it turns out. And one of the many contributions of this paper was to define the notion of EFO. So
I guess I don't know, one way I might have thought of defining this something, an approximation would be to define what is this quantitative value of envy and say that nobody is envying someone much more than the other person is envying them.
right.
It's like
Yeah.
capture it.
Yeah, so you could say, okay, maybe my envy for anyone is at most some delta, whatever, for some fixed delta. Now, this problem it amounts to exact envy when delta is 0. So the computational problem in general is still envy, right? It's generalizing the.
No, I don't just want to upper bound it. I want to say that my envy compared to the other person, like it's like when grass is green on the other side of them. So if I envy the other person for something, they also envy me to a similar value for some other things.
Okay.
So, but I think it's sort of captured even here because what this is saying is,
So you're thinking of sort of distributing the suffering in some sense. So if I envy you, then you better also envy me, otherwise it doesn't make sense, right? I see.
Then maybe everybody has nothing. So I value something, you value something else, I get yours, and you get mine.
That could create actually inefficiencies in the allocation. So we might be better off switching our bundles and these kind of
Actually, for example, this is an example where it's not stable.
This is an example of
Yeah.
the allocation you're talking about actually. Yes.
Both people will be happy to swap their
To swap, exactly. There's an easy improvement there. Yeah. All right. So the reason I'm sort of excited about EF1 is that, unlike exact NVPS, this notion is first of all guaranteed to exist. So no matter what input you give me, there always exists some EF1 allocation for it. And not only that, you can actually have efficient algorithms for computing an EF1 allocation. In fact, there are multiple algorithms for computing EF1 allocation.
The reason without the one good thing, one of the reasons it seems that an MVP allocation will not exist was because of these divisibility weird type issues. 3 goods, 2 people.
Right.
Are those the only reasons why they don't exist?
Those may not be the only. So, like I said, you can have very skewed valuations, even if the number of goods is divisible by the number of goods.
Yeah. What I want to ask is, are there sufficiently sort of natural sufficient conditions that guarantee the existence of NVP?
Yeah. So maybe okay, depends on what kind of natural, but like I said, so for random valuations, right?
Yes.
So if that counts as natural, then with high probability, and you have
Random is natural.
Okay. So that's the upshot in talking to the TIF or audience. Random is natural. So. Okay. All right. Okay. Cool. So let me try to. Sorry.
About random is that it's fair.
I'll actually give an example where random may not be fair.
No, I will go in the Joker.
Okay. So no. Yeah. Okay. We'll see examples of that. Okay. So. All right. So I want to just give you, convince you that we can actually find EF1. Yeah.
In the earlier case, now you have a efficient algorithm, but they make many such solutions, right?
There may be multiple EF1.
You will find all of them efficiently, or just
No. So they can be exponentially many. Exponential in the number of agents and items. They can be very large things.
So enumerating will still be a problem.
Enumerating can be found.
So it could well be that if any free solution exists, it's probably close to this one NVD shifted solution, but that doesn't help you.
Yeah, because I don't have algorithms for enumerating EFN allocations. Yeah. So
But you might still have them in the vicinity, right? I guess.
yeah, but
I mean, I guess NV3 is also this, right?
NVP is a relaxation. Sorry, EF1 is a relaxation of NVP. Yes. But suppose you find an EF1 allocation, it's not clear if you can like make a few adjustments and find something.
That's right. That's right. That's what the exponential thing.
Yeah. And if you put, I think it will contradict that.
That's right.
Exactly. Okay, so let me give you a very simple, very natural algorithm that actually computes an EF1 allocation. I'm sure all of us must have seen it in some of the other contexts. So it's called the round robin algorithm. Okay, and the way it works is that it gives some ordering to the agents, say 1, 2, 3 up to n, and then we ask the agents to take turns in picking the items. Okay, so first we invite agent 1. Okay, it can pick its favorite item from whatever is on the table, and then it goes to the end of the queue. Then agent 2 comes in, picks its favorite from whatever is left, and then goes to the end of the queue, and so on. Okay, and then once we have iterated through the agents, in the first round, then again we start repeating 1, 2, 3,
One item at a time.
one item at a time. Exactly. You can only pick one item, your favorite one from whatever is left. Okay, and this thing goes on until you consume all the items. Okay, very simple algorithm. Turns out that this very simple, very natural algorithm actually gives us approximate fairness in the sense of EF1. And let me try to at least sketch an argument for why that is. So remember, EF1 is a pairwise property. We have to look at every pair of agents. So let me fix some pair of agents, red and blue. Okay. And I analyze the entry of red towards blue. Okay. Now there are two cases, whether red is ahead of blue in the ordering or whether it is behind blue in the ordering. So let's first imagine that red is ahead of blue. Okay. So when we execute round robin, in every round, red would pick an item, and then from whatever is left, then blue would pick its favorite, and then it would be red's turn, then blue, then red, then blue, and so on. Alright. So what we can observe here is that at every round, whenever it is red's turn to pick, the item that red eventually ended up picking and the item that blue eventually ended up picking, they're both on the table. But red nevertheless decided to pick the item that it actually ended up picking. Right? So it must weakly prefer that item over blue's item in that round. Right? And you can make this argument for every round. In the last round, it may so happen that because of the number of items, maybe red gets something and blue doesn't. We don't know. It depends on the number. Okay? But what we can say is that for every round, item for item, red likes its bundle at least as much as blue's bundle. And because of the additivity assumption, it likes its entire bundle at least as much as blue's entire bundle. Right? So it's not too hard to see that in this case, actually, if you're ahead of someone in the ordering, you don't envy not just EF1, envy. Right? So you don't envy the people behind you, you don't round off.
The arrows also not true to the
Exactly. So just by this proof by arrow, I can, for the other case where red is behind blue, right? If you ignore the item that blue picks in the first round, then again, item for item, red likes its bundle at least as much as blue's bundle, right? Except for that item G, right? And that's the one that I would remove in my EF1 definition. Okay?
Do you know if EF1 exists if you are not additive?
Yes, so EF1 exists even for monotone valuations. This algorithm may not work, but there are other algorithms that do.
So you can have any permutation of these pairs and that.
Absolutely,
Yeah.
absolutely,
But
yes.
that will not cover everything.
That would still not cover all the EF1 allocations because one reason is that the kind of allocations you would get from permutation are balanced. People get almost the same number of items, but that may not be necessary. They have imbalanced. Yeah, so Raghu is asking an interesting question. Well, so you seem to be crucially using additive valuations here. And what about non-additive valuations? So turns out you can still find EF1 allocations in polynomial queries, right? But those are different algorithms. Happy to talk about those after the talk.
But still more.
Yeah, even for monotone you can find EF1 using polynomial number of queries, so value queries.
Not even, but monotone is crucial, right?
Actually, in slightly non-monotone models also, under certain conditions you can do it. So I don't want to say that outside monotone is impossible. Actually, it's an open problem whether for general valuations you can find EF1 allocations or not. But there are some special cases in the non-monotone case as well where it can.
Monotone would be of A union B is greater than equal to perfect.
So monotone means that a bigger set is weakly more preferred, set-wise in the containment sense.
More is better.
Yeah. So bigger sets are at least as good for you.
So did you say that you don't know of a case where for general valuation functions
I don't know of a complex
for EF1?
for E4. Yes. For monotone, there are algorithms, but for non-monotone general valuation functions, I don't know complex.
The same algorithm, does it also work for chores?
It does, yes.
Oh.
Yes, it does. Yeah. But again, you need additivity.
Okay.
And again, turns out if you have monotone chores, there is a different algorithm that does work, which is actually in work with about. I'll touch upon over that at the end of the talk. Yeah, that's a great question. Thanks for pointing that out. Okay, is the argument broadly clear to everyone? So I'll actually reuse this kind of argument later in the talk. So I hope we are all happy with this. Okay.
Any other nice algorithm?
Sorry, no, yeah. So I just wanted to say that, EF1 is great, but sometimes we are still not happy, we want more in life. So that was going well, my segue into the next one. That's something.
No, I said any other nice algorithm with different flavor of EF1.
Yes, so you can actually do some kind of matchings. So everyone sort of is pointing to their favorite item. You can do some repeated elimination, and yeah, if you do it carefully, you can actually get EF1 even through matches. You don't have to do round robin. There are ways to do it. So the algorithm that Raghuvanshi was alluding to was for monotone. There is an algorithm that repeatedly sort of iteratively assigns items to the unenvied agent. So they have this greedy nature somewhat. So there are actually many simple algorithms that give EF1. Yeah. Okay. So EF1 is great, but sometimes we are not excited. We are not satisfied with EF1. We need more in life. Why? Let me try to motivate that. Suppose there are two agents, red and blue. Okay. Now. Think of a setting that sort of happens over time, an allocation that happens over time, where let's say on day one, a bunch of candies appear, right? And you have to divide those candies in a fair way between these two agents, right? Now you have just learned about EF1, you apply round robin, right? And it gives you something like that, right? Which is EF1, great, we can all go home. But then again, on day two, again some resources appear, again you apply your EF1 algorithm, right? And sure, on day two, this is EF1, right? Just prove that, okay? And hopefully now we can see where this is going, right? So if this happens over time, and if you're using, say, deterministic algorithms, then the NV can actually build up, right? So you might end up systematically discriminating against certain agents, okay? And this actually motivates thinking about randomized algorithms. Right, as some people sort of alluded to earlier.
Sorry,
yeah.
What are you hoping for?
Yeah, so I haven't actually told you what we're hoping for. It just visually looks very unfair, right? Because the red agent is gathering too much stuff, and blue's NV is kind of building up over time over the red.
But if we kept the sequence,
We could have played around with the sequence, but you can create. I'll actually give you some other examples.
This is the setting where the red player is
always goes first. So it's red, blue, red, blue, red, blue always. Yeah. So if you use that deterministic round robin, it might lead to these unfair looking allocations. Right. Okay. So given this limitation of deterministic algorithms, let's try to expand our search space. Let's think of randomized algorithms. Okay. And perhaps the most natural starting point here would be to say, okay, why don't we just uniformly randomize over all permutations of agents under the round robin algorithm, right? To give every permutation an equal chance. That sounds like a fair idea, right? Okay, so I'm going to argue that even this very fair looking idea might be in some sense unfair. Okay, so let's see how. So suppose again we have this very simple instance, three agents, three items, these are their values. Okay. Now let's look at all three factorial permutations of these agents. Okay, so believe me, these are all here. Okay. And let's say we run round robin with respect to each permutation. Then again, you can believe me that agents will get the items that I have shown below them. Okay, so just as an example, suppose we run this formulation. If it is blue's turn to go first, it would pick A because that's its favorite, so it gets A. Now, if A is gone, then only B and C are left, and if green is the next, it would go for B, and that leaves C for red. Okay, so you get this allocation. For others, also you can similarly get it. All right. So now imagine that you consider a uniform distribution over these 3 factorial allocations. Okay. And what that gives us are these probabilities. So what I've written here is the probability with which each agent gets an item across this distribution. So again, just to check the numbers, so let's say we're looking at red for item A, so it gets A here, and A here. Okay, so 3 times 1 over 6. Okay. All right, cool. So this is the distribution that gets generated when we uniformly randomize over all round robins. Okay. All right. So let me set that aside and let me bring back the values. Okay, so just to remind you, these are the values here, and those things are the probabilities, the allocation part. Now, because we are talking about distribution, it makes sense to evaluate the expected values, right, for the randomized bundles that people are getting. Okay, so let's look at that. Let's look at red agent's perspective. So I'll just look at this row here. Okay, and let me evaluate red's expected value for its own bundle or its own randomized bundle, and compare that with green agent's randomized bundle. Okay. Yeah,
Now this is a problem because whole bundle is a problem.
Yeah, so I use bundle
Really say
as a distribution. Yeah, my distribution.
Because you compare the expected value.
Absolutely.
But this problem actually existed even before.
Yes.
Because
So, yeah.
E of one, but the distinction between the valuation one is getting with respect to other. And then
Absolutely.
Absolutely.
Yeah, so I'm just using it to motivate that in addition to EF1, we need some additional property, and this will hopefully motivate them. But yeah. Okay. Cool. So let me evaluate these expected values. The expected values would be just the product of these 3 values with these 3 over here. Okay, term by term. Okay, that comes out to be 4.5. Okay. And similarly, if you look at red's expected value for the green agent's distribution, it's randomized bundle, that comes out to be 5. Okay. And that seems problematic, right? Because that means that red actually is envying green in expectation. Right? So we started with this. Yeah.
Can you go back?
Yeah.
How are you computing the second thing?
So I'm looking at red's value for green's distribution. So that's 7 times value for A times the fraction of A that you get, plus 6 times value of B times how much of B you get, value for C times how much of C you get.
So green's bundle would have been
It's a distribution.
5, 6 many times green would have gotten B and
Yes.
1, 6 many times.
Exactly. So this is like the randomized bundle. It's not the deterministic allocation anymore.
Aditya, you could have asked this even just for EF. Is there a randomized allocation under which EF is? EF
So that usually is straightforward. Why? I could bundle up all the items and toss a coin with probability 1 over n and give it to the n agents. Right? Then my distribution is the same as that of any other distribution. There's no ingredient expected.
Okay.
But there's a very obvious problem here that for any realization of the coin toss, the entire stuff goes to one person or the other, which is as unfair as it gets. Right? So that's exactly going to be the motivation that I'll present in just a minute. Yeah. Good. So the takeaway from this example is that we started from a very fair-looking distribution, which is a uniform distribution over all round robins. But even that seems to be unfair in this sense that there is some expected envy even under that very reasonable-looking distribution. Right? And that motivates us to sort of formally think about what does it mean for a randomized allocation to be fair. Right? You need to formalize that idea. So just to make it concrete, so what is a randomized allocation? It is nothing but a probability distribution over deterministic allocations. Okay. So for example, if you imagine that this allocation here occurs with probability 1/4, and this allocation here occurs with probability 3/4, that's a distribution over deterministic, and so it is itself a randomized allocation. So that's the sense in which I'll talk about randomization. So one property that seems to be very natural given the example that we just saw is that no agent should envy another in expectation. Okay. Because economists like Latin, they like to call it ex-ante fairness. Okay. So this is ex-ante means before the coins are tossed, your distribution should be fair. And this is the sense in which we talk about fairness.
Yeah, economists consider this sort of, I find it strange because why do I care about my enviness in this expected world? I care for each random point allocation is where I care for.
We care about both of those things actually. And that's the best of both worlds ideas. Yeah, I'll come to that on just the next slide. So just give me maybe like 10 seconds.
More ways to make me feel unhappy.
I'll try.
That is how that would really need to know the actual numbers, 5, 6, 7, the preferences in the thing. You'll probably propose something where you're going to use those numbers and buy the public.
So I mean, if you don't know the numbers, then
Because people normally don't know, they have preferences. If you show them two things, they know which one they like more than the
oh yeah,
other.
so I think right. So I'm making a very strong assumption that you know the numerical intensities of that.
That's right. It's very
Often the definitions are given at an ordinal level, just in a comparative manner.
yeah.
So the definitions I'm presenting are somewhat more cardinal sensitive actually, but ND3ness, EF1, etc. You can just as well define them in an ordinal sense because they're only based on comparing my bundle with your bundle. Sorry. Right. So definition wise, all of this goes through, but my example is probably using the numbers more careful way. The algorithm that I'll talk to you about in just a few minutes actually still works even for ordinals.
So you could develop this whole theory where you kind of just have this model.
Yes, absolutely. Yeah. All of this can be generalized to that side. Okay, so suppose we are aspiring only for this ex-ante notion of fairness, where no one should envy another in expectation, as Prahlad was talking about. Turns out that may not be a very satisfactory notion in and of itself. Why? Because, well, this very natural algorithm sort of, seems to fail this notion. And also there is an unnatural strategy that satisfies this notion, which is to bundle up everything and equi-distribute it, with equal probabilities among all the agents, right? So this seems fair in the sense that everyone's distribution is the same, but any realization of it is as unfair as it gets, right? So that's what it is. In and of itself, it's not a very satisfactory notion. Okay. Which is why we would also like to think about ex-post fairness, which is fairness after the coins are tossed. Right? So remember, a randomized allocation was a distribution over deterministic allocations. Right? Under ex-ante fairness, I'm asking that the distribution is fair in expectation. Under ex-post fairness, I'm saying everything in the support of the distribution is also fair. Now, because we are talking about deterministic allocation in the support, I can't ask for NB-fairness. So I'll have to sort of tone down my fairness requirement, and EF1 looks like a good idea. So in our exposed fairness requirement, we'll say that every deterministic allocation in the support of our randomized solution satisfies EF1. Okay.
So isn't it saying that you're probably randomizing over deterministic algorithms which have EF1?
Yes, I want to construct a distribution only over EF1 allocations. Yeah.
But that's what we have for exposed fairness.
Yes, so far.
So that means if I have just one deterministic algorithm, it's exposed fair.
It may not be ex-ante fair.
Or you want both?
I want both. Yes, that's the key here. Yeah. Okay. Right. So this motivates this best of both worlds property that we want both ex-ante and exposed fairness simultaneously. Okay. So we have seen that you can get one on its own very easily, but we want both. Okay. So the main result that I want to talk about is that there is a positive answer to this question. You can show that for additive valuations, there always exists a randomized allocation, i.e. distribution over deterministic allocations, which is fair in expectation. There is no NB in expectation, and any realization is EF1. Okay. And also, not only does such a solution exist, you can actually compute it in polynomial time as well. So I'll give you another.
I'm just wondering why the following really stupid thing. I mean, can I just try just cyclic shifts of a single permutation? Like I was trying to, I want to do the round robin allocation, but keep track of who went last.
Okay.
Intuitively, that's what I'm trying to do. So I want to just repeat that. Okay.
So you would take one,
But what
I don't want to take all permutations.
But what's your distribution?
The distribution is all for it's a uniform distribution on the cyclic shifts of one.
Small number of permutations.
Yeah.
In possible choices.
Yeah.
in vector.
I mean, I'm trying, I mean, I want to do the old allocation, but
You want to give the last guy a chance and
yeah, I
put
mean,
them
like,
up the queue
the
basically.
last one to pick was me, so I want the one after that to go first.
But then it is, suppose you have many agents and one comes before two, then in n minus one of your cycles, one will always be n be favored two. So you should be better. Two should feel bad for.
Oh, okay. Okay.
So you mean a cyclic shift or like the reverse permutation?
I mean, I read the cyclic, but I think that's a problem.
Oh.
You're saying it's not ex-ante.
Oh, then why don't I just do the following? Just put the support of this order and this order. Oh, either, no, both are it's here.
Both of them are equal. But I don't see why the equidistribution would be here because you may not get that's what I
More often than not, you still NB there.
Yeah, that was counting because when I'm talking about the ND of let's say I versus J, it unfortunately depends on what the other people do.
Absolutely.
So, I mean, it's not a symmetric situation.
Yeah, exactly. Okay, cool. So in the rest of the time, I'll just try to argue, try to prove this result to you. And the proof sketch is actually going to be by an eating idea. So I know this is sort of a post-lunch talk, but I apologize for bringing out eating. Oh, okay. Yeah, sorry for the distraction. Okay, cool. So actually, this eating
Yeah. So the items all have the same valuation.
Yeah.
Was this even a was there a counter example of this type at some point of time?
So if items have all the same values, you should. So let's say you have 3 items, all valued 1 by 2 people. Right? So then it's very easy to construct an ex-ante exposed distribution. You could give 2 items to one person and 1 to the other in one case, and then the other.
Which is what will happen in the fair enough. Yeah, these 2 orderings will take care of.
Yes. So in that sort of flattened out case, it would work out. Yeah. All right. So the algorithm that I'm going to talk about, I'm going to refer to it as the eating algorithm, but it actually has a name in the economics literature. It's called the probabilistic serial mechanism, and it's due to a 2001 paper called by Bogomolaya and Mula. And we'll see how this algorithm actually works really well for our best of both worlds problem. Okay. So let me try to describe the algorithm. I've purposely drawn Pac-Man graphics because it's about eating. So let's say you have these 2 agents, okay, and let's say you have these resources, which are candies in this case, okay, and these numbers denote the valuations. So let's draw a timeline, okay, that goes from 0 minutes, half minute, 1 minute, all the way to 2 minutes. So I'm going to time who eats what as the algorithm progresses. Okay. So suppose both agents start eating their favorite remaining item at equal speeds. Let's say 1 item per minute. Okay, so they sort of gradually start munching their favorite item. Okay. Now, because in this case the favorite item is the yellow candy, that means after half a minute, both agents will have half of the yellow candy, and it will be completely finished.
The rate of eating is the number of items or based on the value for the
Number of items.
It's based on the number of items. Yeah, but it has to be more importantly equal. That's the key. Alright, cool. So yellow candy is gone. Okay. Now red agent's favorite remaining item is the blue candy. For gray, it's the red candy. So now they can eat in an uncontested, non-conflicted manner. Okay. So over the next minute, right, they'll both consume their favorite remaining items. So red consumes the blue candy and gray consumes the red candy. Yeah. And so those are gone as well. And now we're left with green. Again, it will take half a minute to polish them. Okay. So that's how this algorithm works. One assumption that I'll make, that I've sort of implicitly made in this example and that I'll make throughout, is that I'll assume that the number of items is an integer multiple of the number of agents. If that is not the case, I can add some dummy zero value items and run this algorithm and everything will work out just as well. Okay? But for simplicity, let's say these are integral.
So far it is fractional.
Yes, so far what I've constructed is a fractional allocation. Exactly. Exactly.
It is optimizing some continuous problem, correct?
Not really. It's like it's a greedy,
Yeah.
greedy strategy. Yeah.
But yeah, potentially if you just relax the problem, be continuous, maybe greedy side is optimal.
Optimal how?
That I'm hoping you tell
If you put fractionally associated, then you start asking for yes.
For a fractional allocation, it's very easy because every item I can sort of uniformly give with probability 1/n to everyone. So that's easy, right?
Yeah.
What is really challenging us here is we also want exposed fairness. So we want this randomized allocation to be decomposable over fair solutions. So that's the non-trivial bit here. Okay, cool. So what I'm going to do is I'm actually going to rewrite this allocation, whatever just happened, in a more compact and easy to use manner.
By the way, is it?
Yeah,
I assume that allocation which you do, that's going to be the distribution.
it will be absolutely.
Even so, now you had to actually tell me what the support is, which you're possibly going to do that. But is it clear it's actually ex-ante fair?
Yes, so
From right from this way?
yeah,
Rather than 8 for the same amount of time.
because for every time window, what I eat is the best for me compared to what you ate. So I like my bundle at least as much as what you. So the ex-ante fairness should become clear already. Okay. Okay, right. So just to sort of represent it in a more sort of easier to use manner, what I'll do is I'll create a matrix, right? I'll the columns of which are corresponding to the items. What I've done on the rows is that I've created a copy of every agent corresponding to every 1 minute time window. Okay, so because my algorithm ran for 2 minutes, I've created 2 copies of the red and 2 copies of the gray agent. Okay, and each copy will capture what the agent ate in that time window. Okay, for example, if you just look at the first copy, which is the first minute of the algorithm, then we know that red agent, the top ribbon here, it ate half of yellow and half of purple. So I put 0.5 here and zeros elsewhere. And likewise for the gray agent.
That's why you want the number of.
Exactly. Yeah. That's the whole thing. Likewise, in the second time window, so minute 1 to minute 2, I'll again capture what the agent ate in that time window. Okay, so red ate half of purple and half of green. So I put halves here and zeros here, and so on. Okay. All right, so I'm just sort of rewriting the fractional allocation that we have generated so far. Now, the reason I'm doing that is because this matrix now has a very nice form. It's a doubly stochastic matrix, which is to say that every column and every row sums up to 1. Right? Why? Because I have 1 unit of every item. So all these numbers must add up to 1 because 1 unit was completely consumed of that item. And why is a row equal to 1? Well, because I'm looking at 1 minute window and everyone is eating at the rate of 1 item per minute. So the total fractional stuff that anyone ate is exactly equal to 1. That was the reason for breaking this down in this specific. Okay. Now, whenever we see a doubly stochastic matrix, light bulb should go in our heads, which is we use Birkhoff-von theorem, right? And Birkhoff-von says that any doubly stochastic matrix can be decomposed as a convex combination of permutation matrices. So a permutation matrix is a doubly stochastic matrix in which the entries are 0 or 1. So you don't have these fractions. You have 1 in every column and 1 in every row. Okay. And convex combination means that you can just write it as a sort of a scaled version where the scalars add up to 1 and they are not negative. Just like affine combination, but with the condition that they add up to 1. Okay. Alright. Okay. So if I apply Birkhoff-von-Neumann on the fractional allocation that I have constructed so far, what I get is this. So on the left is the matrix that we created, the W stochastic matrix. And on the right, we get the decomposition, which says that this matrix is equal to half of this permutation matrix and half of that permutation matrix. Now, these coefficients may not always be half. I've just conveniently set my example so that they are half, but there could be many allocations in the support, and these coefficients could be whatever. Okay. Sorry. But what you should know is that all the decomposition can actually be done in polynomial time. That's the important bit here. Okay. All right. So now I have to, what I want to show to you is that I basically solved the problem, which is that this convex combination, I can interpret it as a distribution over deterministic allocations, which has both properties that I was aspiring for, ex-ante and ex-post trends. Okay. So what is the transformation? Well, every permutation matrix, you can interpret it as an allocation. Why? Because every item is going to exactly one agent. There's only one in every column. So you can think of it as a valid allocation, right? And these coefficients are probabilities, right? So you can interpret this object on the right hand side as a distribution over deterministic allocations, right? Which means what I really need to prove to you is that every such allocation in the support must be EF1, okay? And that this randomized allocation is itself EF, it's ex-ante NV.
So are you going to show that any permutation matrix is going to be EF1? Or
no ones, the ones that result from my decomposition.
Anything, and any permutation matrix which was sitting in the support of this could have resulted. So yeah, that's what you're
exactly. Yeah. So the decomposition may not be unique.
Yeah.
There may be multiple decomposition. I'm saying pick your favorite decomposition, pick anything in the support. I'll show that it's here. Yeah. Yeah. Thanks. Okay. Okay. So let's see why that is. I hope ex-ante NDP is clear just by the semantics of the eating idea that at every point of time you are consuming the best for yourself, so you should not envy what anyone else is doing. Okay. I just sort of handmade my way through it. I guess the more interesting property is ex-post EF1. Okay. So let's fix any allocation in the support. The argument is similar for any other allocation. So why is it ex-post EF1? Anyone wants to venture this? Why might it be exposed to EF1?
Round robin.
Yeah.
Permutation.
Yeah, this is a permutation matrix, but I can think of it as an allocation.
That's an abstract.
Oh yeah, so the top
only
two is first round and second one is second round.
So say it again, sir.
So the top two rows are first round, or the bottom two rows are the second round.
Right. Yeah, exactly.
the round robin first round, that should work for any permutation.
So in general,
in this case, they are picking their favorite.
Yeah.
Something has to happen.
No, at the moment, this permutation matrix doesn't seem to be related to the valuation at all.
Correct.
But
So
the
something
point was, whatever, Pink Pac-Man went for the blue chocolate because the blue chocolate was the most interesting.
exactly. The fact that it is in the support of the fracture allocation means that when the red agent was consuming the purple candy, right? Red was still available because this is what was consumed by the gray in the second time window, right? But that should tell you that red prefers purple candy over the red candy because some fractional stuff of the red candy was still on the table. It just chose to consume the purple candy. Right? So more specifically, for any round T of the eating algorithm, so by round I mean the time window, the first minute, second minute, and so on. You can show that for any agent, let's say red agent, the good that it is assigned itself at time T, it prefers that over the good assigned to anyone else in a future round. Right? And this is exactly because these numbers are in the support of the eating allocation. So that's that tells you that something about the eating preferences from which you can infer the allocation here. And this looks a lot like the round robin trope that we saw earlier, like item for item, you prefer your bundle over the bundle of anyone else, right? So again, subject to the removal of this item here, you prefer by additivity your entire bundle over the entire bundle of the other item.
So what problem were Boolean solving when they introduced problem?
They were looking at looking at these ordinal fairness notions. They were not concerned with best of both worlds. They were like, okay, we just look at randomized allocations and see what properties sort of go well together.
But they observed these things that.
No, EF1 was not, EF1 was 2011, Muller was 2001.
But there is stochastic property and all.
No, so Berkoff von Neumann is sort of new to this here. They just gave the eating out. Yeah. But turns out that that's just the right idea for this guy. Okay, so I hope everyone is broadly convinced that this is ex-ante exposed EF1. Okay, so I just want to wrap up by discussing a few open problems and directions to future work. So what I've given to you so far is this result that ex-ante EF and exposed EF1 can be achieved for additive valuations over goods, meaning the numbers are positive. So there are various ways in which we can think about extending this result. Well, first of all, as Vaish was thinking, why are we focusing only on additive? We should think of maybe more general valuation classes. And these are some of the more popular ones in the literature. So additive is sort of sitting right here. It's somewhat of a restricted valuation class. There are generalizations such as submodular, then subadditive, and then monotone. Monotone is sort of like the most general when it comes to goods. Now, it turns out that even for the most general class, you can find exposed EF1 alone in polynomial time or polynomial queries, right? So the challenge now is to extend this result to, let's say, monotone valuations. For monotone, can we find ex-ante plus exposed EF1 together? Right? So that's, I think, a very nice question to think about. Another question could be to think about the exposed fairness notion, right? So I presented the EF1 notion, which says there is some item in the other bundle that you could remove. But you could think of a different quantifier. You could say, I want to remove my NP up to the removal of any item, right? So that's called the EFX notion, and we feed up to any word. And so EF1 says if I envy you, then there exists some item in your bundle I can remove. This notion changes the there exists to forever. So no matter which item I remove, I should not envy you. So it's a much stronger notion.
That may not exist.
Oh, it's a great question. I see Kavita smiling. Yes, so turns out, proving the existence of EFX has been a very challenging problem for a few years now. The best results that we know for EFX are that up to 3 agents, we can show that EFX exists. So I'm not even talking about ex-ante anymore. I'm just talking about EFX. For 4 or more agents, we don't know. Right?
Whether it always exists.
Sorry?
Whether it always exists.
Whether it always exists or whether there is a complete sum, we don't have either a proof or a complete sum.
Or even for additive groups.
Even for additive groups, yes. Yeah. So all of this is for additive. Right? Even for additive, we don't know. Even if you have a lot of goods that have 0 values.
I mean, you're saying
You could give all the 0 value goods to maybe one agent, and that should not be anything. So yeah, so
One sale
One sale who doesn't exist.
yeah, so I mean, there's work by Kavita and others on approximations of EFX, which is EFX with charity. Meaning, if you discard a small number of goods, give it to some other agent who doesn't care about the worldly affairs, then you can get the effects of the rest of the goods. So by discarding a small sublinear number of goods. If we can relax assignments, then even I can solve the EFX problem. So yeah, we have to assign everything, and And Kavita's work and some other papers have also shown that if you don't assign a small subset, a sublinear related subset, then you actually can get effects for the rest of the equation. Right? So those are kind of the best results that we have so far. We haven't managed to crack the apex problem for 4 agents and beyond. Right? So I'm saying let's add to the difficulty of this question by even asking even for ex-ante fairness on top of that. Okay, so that's one question. And actually, in some work with Kavita, we have shown that okay, if you are looking at a stronger notion than ex-ante EF, then it may not be compatible with exposed EFX. Okay, but what happens with ex-ante EF and exposed EFX, we don't know. So that's a very nice open question. Again, I'm happy to talk about the exact specifics later on. Okay. The third question I want to
computational aspect.
actually here even existence is a challenge.
No, but it might be that what is it? Like you still don't know whether it exists, but if it exists, it might be hard to find.
What does that mean? No, so basically, NP hard means that there is no instance.
Well, I can give you, I mean,
You mean like a unit reductions or?
No, I guess we want, I mean, Saturday is probably asking for a promise.
Yeah.
Like,
Even the promise instances. I'm actually not sure. I don't know for promise instances. I haven't come across any such computation. So given the struggle that we have had, even with existence, actually computation seems.
No, but those two might be different.
I see.
Coming to that, so is there any structural thing on the valuations which will guarantee for which we know EFX exists?
There are some results which say that okay, so one result I can tell you about is let's say your preferences are lexicographic, meaning you like item 1 really much, so much that you'd rather have item 1 compared to all the other items. You really like it, right?
Okay.
Subject to that, you'd rather have item 2 compared to any other item. So any bundle containing item 2 would be preferred over anything else. Subject to that, item 3 and so on. So these are lexicographic preferences, like dictionary ordering.
And everyone has their own.
Everyone can have their own lexicographic ordering. Under this very strong assumption, you can actually get polynomial type algorithms for EFX. But yeah, I mean there are other results of this form as well. But yeah, we don't have general additive valuations. We don't.
What are the random valuations?
So random valuations, even EF exists with high probability, so it's stronger than EFX. EF is the strongest notion, then EFX, then EF.
Probability doesn't exist.
Yes, yeah. But yeah, I mean, people have actually done a lot of computational experiments. No one has found a counter example. Things like
So for EFX, we shouldn't have like one goal which is all zeros, right? Because anyone can give it to it.
So you should give it to someone who is not envied so far.
All zeros you can just discard. You can.
Yeah.
Is there any hope that economists will apply the idea of
This is going on streaming, so let me not make any control. There might be economists watching for all this.
getting background insight?
No, I mean, so actually there
I've
are.
been using Reddit and so on.
Yeah, exactly. So there are websites which have implemented some of these fair division algorithms, not this one, but some others that probably give these approximate indicators guarantee. And people seem to like it. I mean, they're like, okay, there's something.
What's the context?
There is an app basically that where people have implemented algorithms from the academic literature. Right? So for
Sometimes
example,
even taxi fares.
Yeah,
Yes.
So there's this strong thread also. So the very nice.
I think the website is currently down.
No, that's a different thing, but these are all like theoretical fair algorithms. So
Yeah, it's
And then complete some other thing.
yeah. Implemented brand division, but we are losing out on 2 brand lists. For do fair and lovely and now.
Yeah, that means streaming. So I'm very worried about that. Okay. Another problem that I want to mention is that, and this is one that economists really like, is Pareto optimality. Right? Pareto optimality says that there should not be an obvious improvement on your allocation. Pareto improvement is a way of redistributing the resources such that no one is worse off and someone is strictly better off. So if you could improve someone without harming anyone, why wouldn't you do it? Right? And if there is no such improvement, you call your allocation Pareto optimal. And wouldn't it be nice to have ex-ante indivisibility along with exposed EF1 and Pareto optimality, right? Now turns out that EF1 and PO alone, if you forget about ex-ante, right, just exposed EF1 and PO alone, there do exist allocations that satisfy both of these notions. So fairness and efficiency can go together in this sense. We know that for additive evaluations, such allocations always exist. Now the question is, well, can you construct an NV-free distribution on top of such allocations? So again, that is a very, very nice open problem. And the final one that Ramprasad was thinking about is, what if your resources are not desirable, they are undesirable resources, like grading exams or whatever. How can you talk about ex-ante and exposed fairness guarantees? Now, turns out in that model, if you have additivity assumption, then a very similar algorithm actually gives you ex-ante EF and exposed EF with a very similar code. But again, one could think of generalizations like beyond additive and EFX and EF1 and EF1, etc. So we don't know actually much less about code than we do for those in general and specifically for this problem. So let me, by the way, so for monotone shows, EF1 allocations always exist. This is with the one, right? So again, you have exposed EF1, but what about ex-ante? Yeah, let me stop here. But you can take yours. Sorry, I didn't catch that.
Questions, otherwise you can have questions over time. I think questions for the
current note, the EF, just asking about care is just anything is at the level of an entire comments to make. So a stronger notion would be maybe some notion of stability, not that. I don't envy your bundle, yeah. But we are actually better off like swapping one item of yours to one item of mine.
I see. Okay.